Hi everybody, this is David Van Vranken here at UC Irvine, and this is our 9th lecture in the Chemistry 51C series. I ran into this video recording of Derek Barton talking about conformational analysis, and so I wanted to start off our lecture just by hearing him talk about something that had such a dramatic impact on the field of modern organic chemistry and modern organic synthesis. And let me see if I can play this.
The work of Hassel taught us how to choose a preferred conformation for cyclohexanes and for decalins. An extension of this procedure enables us to choose preferred conformations for polycyclohexanic systems. For example, the steroid nucleus, which consists of 3 6-membered rings joined together, has a unique 3-chair conformation, which is the preferred conformation. In order that I may explain to you the conformational analysis of the steroid nucleus, I must first of all introduce the nucleus and tell you a little about nomenclature. You see 2 angular methyl groups, and these angular methyl groups are thickened in the formula here. This thickening means that they are pointing towards us from the plane of the paper. This applies also to other substituents which have the thickened bonds. Substituents with the dashed bonds, on the other hand, are pointing away from us, away from the plane of the paper. We designate the first kind of substituent beta. They are on the top side of the molecule, and we indicate the second kind of substituent as alpha, and they are on the underneath side of the molecule. You see clearly the 2 angular methyl groups on the top beta side of the molecule, and you see the alpha side of the molecule, the underneath side, where there are no methyl groups. The consequence of having 2 methyl groups on the top side of the molecule and no methyl groups on the underneath side is that reagents tend to attack the steroid molecule from the underneath side, that's the alpha side, rather than from the top side, which is the beta side.
Okay, here we are on, again, this is Derek Barton. He was a winner of the Nobel Prize for his work in conformational analysis. And here's a picture of him posing in his lab, holding, you can barely see it because the metal or the model he's holding is so thin. But he's holding onto a model trying to talk about conformations. And we have not spent a lot of time talking about this. When you took the first quarter of organic chemistry, you learned about chairs and chair-shaped conformations, but really it was the work of Derek Barton that really moved this to the next level. And I want to take you back to the work that really preceded his. I think he referred to this. It was work of a Norwegian chemist named Odd Hassel. And it was Odd Hassel who really started thinking about chair-like shapes of cyclohexanes, especially when they are fused together. And so what Odd realized is that, and I love this picture of him over here. He's standing around in his lab holding a cigarette, smoking, and something you definitely could not do nowadays. But when you fuse 2 6-membered rings together, 2 cyclohexanes together, we call this particular compound decalin, has 10 carbons. There's 2 different ways you can join those 2 rings. At the ring junctures, you can have 1 hydrogen down and 1 hydrogen up, as I've indicated here, or you can fuse those 2 rings together so that both hydrogens are down or both hydrogens are up. So trans-decalin or cis-decalin. But the consequences are dramatic for those 2 rings, because as you can see here in these pictures, when you have the trans-decalin, the molecule is quite flat, or reasonably flat. But when you fuse together the 2 cyclohexane rings so that you get cis-decalin, the molecule adopts this very bent shape, almost like a chair. And this is really fundamental, this idea that stereochemistry can have such dramatic consequences for the shapes of molecules and for the directions in which reagents attack. That's what Derek Barton was referring to. So it may not be obvious to you that if I place another functional group over here, like a methyl group, and I draw that with stereochemistry up, what you can't tell is that that methyl group is now badly bumping into this CH2 group over here. There's a dramatic steric interaction. And unless you're able to draw out conformations like the ones that we've shown over here on the side, it's hard to appreciate why that should be the case. So what I'm going to do is I'm going to draw, using conformational principles, analysis principles here, these two systems. So here, this would be cis-decalin, and the two hydrogens would be on the bottom face of those ring systems. And now when I hold it like this, you can see that if I had a methyl group here, this is occupying the same space as the CH2 group on the other side. They're literally bumping into each other, trying to push the hydrogen atoms into each other. And so this is the work of Hassel and David Barton, is realizing that when you had, for example, methyl groups on the beta face of this molecule, which means pointing towards the viewer, that in some cases, if you understand the conformation, you can have dramatic steric interactions that control reactivity. This turned out to be a super important point once chemists in the 1950s started to work on steroids. Steroids are a particularly important class of small molecules, and they have this 4-ring framework that's composed of 3 cyclohexane rings and then 1 cyclopentane ring. And so a classical steroid has 3 different ring systems associated with that. And if we draw these out, they would look like this. This would be a classical steroid ring system with 4 rings called the A, B, C, and D rings. And understanding the shapes of these molecules, and that some groups, like these angular methyl groups here on the top, or the beta face of the molecule, understanding that those would be on one face, whereas other substituents, like over here, might choose to be either beta, which is up, or alpha is down, really tells you about the shapes of those molecules, and helped chemists to design powerful steroid medicines, the birth control pill, corticosteroid molecules to fight inflammation. So when you look at these molecules in biology, steroids turn out to be super important. Here's a picture of an androgen receptor. This is the ligand binding domain from the androgen receptor. This is a transcription factor. It controls the transcription of genes. That's why steroids are so important and so powerful and potent. You only need tiny, tiny amounts of these types of molecules, of steroids, androgens, testosterone, corticosteroids to exert biological functions. And when you look deep inside the binding site of this androgen receptor, you can see, in this case, it's testosterone kind of embedded in there. If you could just kind of squint your eyes and look closely. And you can see those methyl groups on the top face. You don't need to get a crystal structure of this molecule to know the shape of the testosterone. The principles of David Barton and Hassel allow chemists to tell you exactly what the shape of the molecule is going to be. Just with a pencil and paper and drawing out some chairs, you can guess the shapes of the molecule. Okay, so conformational analysis, super important for the field of organic chemistry. Being able to draw chair conformations is super important for being able to predict the structures of polycyclic molecules. Okay, let's go ahead and move on now to our lecture for today. We're starting a new chapter here in Chemistry 51C in the Gorzynski-Smith textbook. And this chapter is, just like the last chapter, is about the reactions of carbonyls. But in this chapter, most of the chapter is associated with weaker nucleophiles. In the last chapter, we learned about organometallic reagents, like organolithium reagents reacting with carbonyl groups and attacking, and hydrido reagents reacting with carbonyls. We had a little bit on cuprates. But in this chapter, it's mostly weaker nucleophiles. There's one exception towards the end when we talk about phosphonium ylids. But let me introduce you to part of this chapter. This chapter is really focused not on esters, but on aldehydes and ketones. And I want us to start off by contrasting the reactivity of aldehydes and ketones by comparing them with carbocations. Let's start off with something you should already know about, and that is the more substitution that you have on a carbocation, such as primary, secondary, and all the way to the tertiary, the extra substitution increases the stability of those molecules. So whenever we have tertiary carbocations, they are more stable than primary carbocations. You should already know that. So tertiary carbocations are more stable. More substituted carbocations are more stable. They're also more hindered. Now, carbocations are so reactive. Right? Hindrance doesn't usually stop a carbocation from reacting. Maybe SN2, but not additions to carbocations. But the end result of these two effects of being more stable and more hindered is that tertiary carbocations, in theory, are less reactive than primary carbocations. Now, their carbocations, again, are so reactive, you're never going to see the effects of this. But this same trend is something that we're going to see with carbonyl compounds. If we take carbonyl compounds that have two H's versus an H in an alkyl group versus two alkyl groups, as you add more substituents to the carbonyl, it becomes more stable and it becomes more hindered. And as a result, ketones are going to be less reactive than either aldehydes or the parent aldehyde, which is called formaldehyde. So ketones are going to react more slowly. It's just a general trend. So the general trend that we're going to see is that aldehydes, the less alkyl groups and the more H's we have, the reactivity is going to increase in this direction. So not so important for carbocations, which are screaming hot reactive, but important for contrasting the reactivity of aldehydes and ketones. And we'll consider esters and amides separately in the next chapter. We're not ready for that quite yet. Now, the book has a section on nomenclature of aldehydes and ketones. I don't ask you IUPAC nomenclature on my exams. That's not something that I just feel like we have time to address in this class, but I think it's good for you to read, and sometimes they ask about that on standardized exams. Okay, so what do I expect you to know when it comes to nomenclature, right? You know, generally, I expect you to know two common functional groups that aren't always aldehydes or ketones. It also applies to carboxylic acid derivatives. So the general class of functional groups that I expect you to know are called acyl groups. So when you have some sort of an R group attached to a carbonyl, doesn't matter what's here, right? That X could be a nitrogen, oxygen, carbon. I would refer to this as an acyl group. This piece right here, where could be methyl, ethyl, phenyl. That's called an acyl group, that general class. And we've talked about acyl chlorides when we do Friedel-Crafts. You've seen that kind of nomenclature before. But I want to give you two distinctive members of that class of acyl groups where I expect you to know what I'm talking about when I refer to it. So there's one particular acyl group which just has the simplest organic functional group, a methyl group. And this particular functional group is called an acetyl group. I expect you to know that is an acetyl group. So let me go ahead and circle that. That's called acetyl. It's kind of older nomenclature. And it's so common. If I say, hey, that acetyl group, you should know about that. You've probably seen this if you've taken a biochemistry class. You've probably seen a molecule called acetyl-CoA in the Krebs cycle. I hope to gosh you haven't been forced to memorize that. I had to memorize that when I was an undergrad. I'm still waiting to use the Krebs cycle in any aspect of chemical biology or bioorganic chemistry. But that whole acetyl part is just this tiny little piece here, whereas coenzyme A is all the rest of that molecule, which is really the handle for the protein to bind onto. So I expect you to know acetyl and what that means, and biochemists expect you to know what that means as well. There's another common functional group that I expect you to know, a common acyl group that I expect you to know, and that's when there's a benzene ring attached to the carbonyl group. And I expect you to all know the name of this. This is called a benzoyl group. So we would refer to that as benzoyl, whether it's attached to whether X is oxygen or nitrogen. Now be careful, it's benzoyl, not benzyl. Benzyl is something completely different. Benzyl is just phenyl with a CH2 attached to it. But this is a carbonyl group. It's benzoyl. So I'm going to underline that O, benzoyl. You've probably seen this in the stores when you go buy acne medication over the counter. It contains something called benzoyl peroxide. In that case, X is 2 oxygen atoms with benzoyls on both sides. So again, you'll see these, I'll refer to these groups, and I expect you to know what I'm talking about when I refer to acetyl and benzoyl groups. They're two examples of acyl groups. the book has a section that talks about physical properties of aldehydes and ketones, polarity, things like that. You can skim that. I'm not going to ask you the boiling points of any carbonyl containing compounds or the level of volatility. So that's not really important. What I will ask you about on every exam is some kind of a spectroscopy question. And we just don't get enough practice working with spectroscopy in this class. I usually ask one question on each exam, depending, or maybe two on a final if there's time for us to ask those kinds of questions. Now, I find that the book sometimes just gives you a spectra and says, what's the compound? And that's completely unrealistic. You know, in a real research laboratory, you have some plausible ideas for what's the structure of the compound, and you're just trying to rule things out. That's the way we use spectroscopy in a typical scenario in a laboratory, is we use it to rule out, if you've got 5 plausible structures, which ones can you rule out using spectroscopy until you narrow it down to one that matches every single piece of data that you've got. So if I tell you, well, I've got a compound and it's one of these 6 structures right here, you should always use spectroscopy using the simplest stuff first. What's the simplest type of spectroscopy to use? It's mass spectrometry, because it gives you molecular formulas. So if I told you that the molecular formula was this, you know, you could immediately rule out a bunch of these compounds. Once you know the molecular formula has no halogens in it, you can cross out that. Oh, here's a bromine. That's not in the molecular formula down here. Cross out that. You can count up how many oxygen atoms. There's 2 oxygen atoms. Cross out that. Cross out, right? Very quickly, with rudimentary knowledge, just being able to count halogens and oxygens and hydrogens, you can rule out all but 2 of these compounds, and then you can start using the more challenging stuff. So to me, the second easiest type of spectroscopy to use is carbon-13 spectroscopy. So I've use that second. If somebody gives you a carbon spectrum, or you go take one, and why is that powerful? Well, usually you just count the number of carbons, and that's the number of peaks. And if it doesn't match, well, that's probably not the right structure. You have to be careful with carbon and proton NMR spectroscopy to watch out for symmetry. So for example, here's a molecule called xylene over here on the side, and I would expect you to know that these 2 metacarbons over here are identical. They're indistinguishable, even though I've only drawn one resonance structure that makes those 2 look different because of the double bond pattern. I expect you to recognize the symmetry of molecules. I would expect you to know that the 2 methyl groups here have the same chemical shift and would lead to 1 peak in the carbon or the proton NMR for those. What's the third easiest piece of information to use in terms of spectroscopy? It's usually IR spectroscopy. There's not a lot of useful information in IR spectroscopy. You just use it to identify functional groups. So what are some of the functional groups you ought to be able to identify in an IR spectrum? Well, a carbonyl stretch, those are usually big valley type peaks. They occur like somewhere around 1700. I expect you to be able to identify bonds between carbon and hydrogen or oxygen hydrogen. They're down over here on the higher frequency end of the spectrum. And then triple bonds, which are really distinctive. Very few things appear down around 2000 wave numbers. Triple bonds, that's usually nothing in that region. And so here I could say, wow, there's a triple bond in there. Okay, I kind of already had narrowed it down to these 2 choices. The last piece of spectroscopic information that I would encourage you to use would be proton NMR spectroscopy, because it's the hardest. But it's got several components to it, and I would urge you to try to use the integrations first, right? You'll see peaks in there, and does that peak have 2 H's? Well, then it's probably a CH2. Is it a 3H peak? Well, it's probably a methyl group. And for 1H, you know, it's harder to tell what's going on, but use the integrations, right? Once you know you're looking at CH2s or CH3s based on the area under those peaks, right? That's usually simple to think about CH2 groups and CH3 groups. The next thing that I would encourage you to look at in the proton NMR is the chemical shift region. So things down here past 7 ppm, that's usually aromatic peaks down in that region, and lower, you know, at lower parts per million, you know, those are usually not aromatic peaks. The very last piece of information, which is the most obvious piece of information, so it distracts you, is the splitting patterns. That's the hardest stuff to use, because methyl groups and CH2s get split by their neighboring atoms. So even though it's easy to tell that there's 4 peaks in a quartet and 1 peak in a singlet, this whole idea of using splitting, I would save that for last. It's the hardest to use because it's the neighbors that split, and it's hard for you to keep track when you're just learning spectroscopy. It's like, how are the neighboring atoms affecting a methyl or a CH2 or a methine CH? So use the easy parts first. Spectroscopy is all about ruling out structures if you want to use it in the easiest possible and most typical possible way. Now, I want to spend a little bit more time talking about carbon NMR because the book doesn't emphasize it enough, and it's way easier than proton NMR. Generally, you compare the number of peaks in your spectrum to the number of carbons in the structure to see if they match. You'll have to look for symmetry, but here's an example of an estrone. This is a steroid molecule, it has a benzene ring in it. It's an estrogen derivative, and if I wanted to tell whether this compound was consistent with the spectrum, the first thing I would do would be to count the number of carbons and see if it matched, because if it didn't, that's not the right structure. So, but you can also use the regions in which the signals are appearing to get information. And so I want to take a look at how the regions of the C13 NMR spectrum are diagnostic, because it's much more defined in terms of where you see those peaks as to what they mean. So let me start off by looking at everything down here below, about 110 parts per million. In that region of the spectrum, there's not a lot you can say. What you can say is that in that region of the spectrum, that's where you find singly bonded carbon atoms. And it could have halogens on there, H's, other groups. You don't get a lot of information beyond that. It's a carbon with 4 single bonds to it. Okay, and that's what you can see down here is for the steroid. Look at all those atoms that have single bonds in that, that have single bonds to you'd expect all of those carbon atoms to be below 110 parts per million. And you can see them down there. Here they are. And if you counted up those carbons that are singly bonded carbon atoms, it'll equal the number of peaks there. So that's typically between 110 parts per million and 0 parts per million, to about 0. Now up above 110 parts per million, this is where you see things that are singly bonded. So let me go over here and I'll just write, that are double bonded. But that could be either CC double bonds, or it could be benzene rings. They all occur in the same region. You can't tell from the chemical shift whether you're looking at 3 double bonds or the carbon atoms in a benzene ring. So those are carbons that are parts of double bonds. Down over here from about 160, let me just define this region here. This is about 160 to 110 parts per million. That's carbons that are parts of double bonds. Over here, above that region, we have carbonyl groups, and specifically carbonyl groups that are attached to heteroatoms. Let me make this a different color just to make that a little more distinctive and dramatic here. Let me pick a unique coloring scheme here. So here with this, I'm going to call it about 155 to 185 parts per million. In that region, you have carbonyls that are attached to heteroatoms. So that would be X is a nitrogen, X is an oxygen, X is a halogen, like in acyl chloride. Those occur in that region of about 185 to 155. And then finally, when you have carbonyl groups that are attached to no heteroatoms, no heteroatoms, that would be things like ketones and aldehydes. So on the other side of this, it could be either an R or an H. Both of those would appear kind of past 190 parts per million. So maybe very rare to see things past 220. So I'll just say 220 to 190, right? That's powerful that you can tell the difference between an aldehyde and an ester using a C13. You can't as easily tell the difference between the different classes of carbonyl groups by looking at an IR spectrum. Now, I have to be honest with you. There is one annoying area of the C13 spectrum, and that's this region right here. about 155 to 160, where when you see signals there, it's like, wait, is that a carbonyl or a benzene ring carbon? Not so easy to tell. And there's another, in this region, there's one more classification of atoms that fits in this region over here. And I'm going to say that that's about 150, but it's kind of unusual, so I'm a little bit reluctant to freak you out by telling you there's one thing that doesn't fit in that region, nicely into any of these regions, and that's enones. The beta carbon on an enone, that's this carbon right here at the bottom. That carbon right there, the beta carbon, that's where you add cuprates to that. Those tend to occur about 150 to 165 at the way far end of the alkene spectrum. And you can draw a resonance structure that puts a positive charge there. We'll talk more about enones and why they're reactive on that beta carbon. But for the most part, you've got distinctive regions of the C13, singly bonded carbons, doubly bonded carbons, carbonyl groups, and then aldehydes and ketones. Why not use the C13 more? You don't get enough practice with that. There's a section in the book that talks about interesting aldehydes and ketones. I can't even remember which ones they put in there. I'm not going to ask you those questions just to memorize some cool fact, even if it's cool, and then you tell me, because I'm usually asking you about other things in my exams, how to draw mechanisms, how to predict products, how to work backwards and think about starting materials. So those are the kinds of questions that I'll ask in my exams. But I would encourage you to read those parts of the book. Now, to set us up to use the reactions in this chapter, we're going to tell you about how oxygen atoms add to carbonyl groups, especially ketones and aldehydes. Nitrogen atoms add to ketones and aldehydes. Cyano groups and phosphonamylids. So we need to know, how do you make ketones and aldehydes if you have to make them in order to use them synthetically? So let's go ahead and walk through this, some of the reactions that you've learned about and may have forgotten about, because it's good to review and remember what are the reactions that you know how to use. So let's go ahead and talk about aldehydes first. Let's review what are the ways you know how to make aldehydes. The most powerful way to make an aldehyde in this class is to oxidize an alcohol. Well, they gave you so many reactions back in chapter 12 in the Gorzynski-Smith fifth edition of the textbook, but they didn't tell you which ones were more important. What they should have screamed at you was PCC is the most useful reagent in that chapter, because it allows you to make aldehydes and ketones so that you can add Grignard reagents to those. That's the most valuable reagent. If you have a primary alcohol and you treat it with PCC, pyridinium chlorochromate, you get an aldehyde. So you need to know that. I say I promise you, I can't imagine writing exams where I don't have at some point in this course where I'm not asking you to know that fact. Maybe we've already had that on our problem sets. Okay, what's a powerful reaction you learned last chapter for making aldehydes? And this is not so common, but it is super useful. And that is to reduce esters into aldehydes. So, and the reagent that we taught you was a 2-reagent combination. Step 1 is dibal-H, diisobutyl aluminum hydride. You don't even need to know it stands for diisobutyl aluminum hydride. The mechanism is nothing like lithium aluminum hydride. So, and they didn't even tell you what the mechanism was. Don't worry about it. And you follow it with an aqueous workup is step 2. The thing I'm not showing, because you usually throw this away, is the alcohol component that you get as a byproduct. And usually that's ethanol or methanol. And those usually volatilize off at the end of the reaction. You're usually interested in the aldehyde piece so that you can use it for adding Grignard reagents or some of the reagents in this chapter. So you do form an alcohol byproduct in this case when you split that carbon-oxygen bond, but usually we're throwing that away. If I ask you the products, you have to draw both of them. But in the lab, we're usually throwing one of them away. Way back in chapter 11, it was the chapter on alkynes, and it was a lot of that chapter was doing the same reactions you did with alkenes, but doing them with alkynes. And one of the reactions that you learned about in the alkyne chapter was hydroboration oxidation, just like hydroboration oxidation of alkenes, except alkynes gave you carbonyl products. And remember the workup for hydroboration, it's this 2-component mixture where you take hydrogen peroxide, just like they sell in the grocery store, and sodium hydroxide. They're actually synthesizing sodium hydroperoxide by mixing those two things together. I don't know why they don't just draw that. The initial product for this reaction, we're going to talk more about this later, is an enol. And this is going to be 3 chapters from now. You're going to be wondering, how did I live my life without understanding that the initial intermediate is an enol? I don't know, but they don't really mention that much or talk about it. When it finally equilibrates, you get an aldehyde at the end of this reaction. It's not quite as useful as these other, PCC is way more useful, but I expect you to know this hydroboration of alkynes. And you know what's cool is that you know how to use sodium acetylides to make carbon-carbon bonds. So now I'm telling you, after you do that, after you make a new CC bond like this one right here, by adding an alkynyl anion to a carbonyl, you also know how to further functionalize that alkyne. Okay, what's another way to make aldehydes? You can do ozonolysis of double bonds. And if your alkene has H's on the alkene, half that part of the molecule is going to turn into an aldehyde. So here's an alkene that has an H on both of the carbon atoms. And so when you put this through ozonolysis, let me write out the conditions for ozonolysis. Step 1, ozone, that's O3. Step 2, well, you have to do a special workup using dimethyl sulfide, so sulfur with 2 methyl groups on it. And I think I usually write out dimethyl sulfide like this, Me2S, just like H2O, except Me2S. And that cleaves the weak oxygen. They don't show you the mechanism for that. The important point is that this bottom part of the molecule, let me see if I can try to highlight this using orange. This bottom part of the molecule turns into a carbonyl, and then the top part of the molecule turns into a carbonyl. So both parts turn into carbonyl. So if your alkene has H's on the alkene carbons, you end up with aldehyde products in your reaction mixture. All right, let's go ahead and talk about ketones. How do you make ketones? It's kind of, most of all, it's going to be kind of the same reactions I just showed you. What's the easiest way and most valuable way to make a ketone? It's using PCC. It's oxidizing secondary alcohols using PCC, just like we did with a primary alcohol. You don't have to memorize a separate reagent if you don't want to. So you take a secondary alcohol that has a single H on this middle carbon called the carbonyl carbon, and it'll oxidize just like a primary alcohol. Now, in this particular case with secondary alcohols, if you wanted, you could use chromic acid, and it always requires, you can't buy chromic acid. You have to make it in the laboratory by mixing some chromium reagent, chromium salt or chromium compound with sulfuric acid under aqueous conditions. This is called Jones reagent or a Jones oxidation. For some reason, the book likes to give you 4,000 different, or it seems like 4,000 different chromium reagents. It could be chromium trioxide, but if you don't have any of that on your shelf, you could use, whoops, I didn't mean to erase that. You could use potassium dichromate if you wanted. I don't know why you need to memorize that. So if you wanted, you could use Cr sodium dichromate instead of the chromium trioxide, or you could replace that with potassium dichromate. There's no difference as far as you're concerned. Once you mix these with sulfuric acid, you get the same reagent. Why does the book tell you several different things to do this? I don't know. They should just give you one set of conditions and don't mention the fact that you could use a different chromium starting materials, chromium reagent for this chromic acid, to make this chromic acid mixture. You know, I just feel like PCC is easier for you to remember. There will be a case later when you need to use these chromic acid oxidations. That's to make carboxylic acids. We'll wait till later to talk about that. Okay, another reaction to make ketones. Friedel-Crafts acylation makes ketones. It always makes phenylketones. So I hope you know the reagent you use when you mix an acyl chloride with a benzene ring. It should be aluminum trichloride. So my gosh, if you don't know that, you need to know that, because we just finished having an exam on Friedel-Crafts acylation. So you need to know that way to make ketones. And now, after covering chapter 20, I hope you, every time you see a ketone, you want to add Grignard reagents or alkylithiums to that, or reduce it back to an alcohol using sodium borohydride or something like that. Now we can make ketones using ozonolysis, just like we make aldehydes using ozonolysis. It just depends on the substitution pattern of the alkene. So if your alkene has two substituents on a carbon atom, that means the whoops, let me undo that. That means the product is going to be a ketone. And as I mentioned before, if your starting material had an H sticking off the end here, then you're going to get an aldehyde. So whether ozonolysis gives you aldehydes or ketones depends on the substitution pattern that you had on the alkene itself. So what's the reagent used for ozonolysis? I just showed it to you. I'll show it to you again. Step 1, ozone. And step 2, always for making these types of aldehydes and ketones, is dimethyl sulfide. And there was some obscure reaction they showed you where you could work up these reactions using hydrogen peroxide, and in that case you couldn't isolate aldehydes. It would give you a carboxylic acid. We might get to that later. It's not very common. And then the last set of conditions is something I skipped because it just really has no utility in the field of organic synthesis. But the book mentions it, so I'll kind of mention it in case I accidentally forgot to say don't work on this problem because it seems kind of silly. And that is to take cuprates, which I showed you for adding to enones, and adding them to acyl chlorides. So I didn't mention this, and I'm a little bit reluctant to spend any effort to talk about this because it just is not something that people would use. Step 1 would be just to add a dialkyl cuprate into this. There's an aqueous workup, but the reason why this is completely pointless is that no organic chemist would ever do this nowadays because it's a lot of work to make an acid chloride. There's always an easier way to make a ketone than first synthesizing an acid chloride and then mixing that with a cuprate. So I'm just going to write here uncommon, but that's being generous to call it uncommon. So that just means there's no way I would ask you that because I think it's a pointless reaction to teach you. Okay, boy, we've got to get ready. It's going to be confusing because we're learning about all these different carbonyl groups. We're learning about aldehydes, ketones, esters, and you're going to see multiple sets of conditions that are going to make you wonder, how do I decide what's with this aqueous workup step 2? And how come sometimes in this chapter, we're putting acid directly into our reactions while we're trying to attack the carbonyl? I told you don't mix everything together in the last chapter. The water and the lithium aluminum hydride, they'll just go up in flames. Let's go ahead and talk about that. In the last chapter, what we talked about was this idea that if you want to add to a carbonyl compound using an organometallic reagent or a hydrido reagent, that we generally need to separate this into 2 steps. We start off by making the carbon-carbon bond. I lift up the electrons in this bond away from the lithium, and then I give them to the carbonyl to make a new bond. And there we go. So I've got this new bond here. And you'll end up with an alkoxide anion. Now, chemists don't like to work with alkoxides. We don't like salts. Salts dissolve in water. It's hard to get them out. So we protonate these. We swamp it with water. We put in so much water that just by equilibration, all the O minuses get an oxygen. And neutral molecules, we can deal with those. We extract those into organic solvents. And when we evaporate off the solvent, we're left with pure molecules. So we like neutral molecules. That's why we do this in 2 steps. Let me just write that out. It's super important that you recognize that we do this step 1. And then after the reaction is done, several hours later, you come back and you pour in water into the reaction. And you would never, ever put water in with your alkylithium. It would destroy the alkylithium before any ketone addition happens. But what we're going to find in this chapter is that we're going to be teaching you conditions for adding weak nucleophiles. Weak, especially oxygen. Weak oxygen nucleophiles. Water, alcohols, they add slowly to carbonyl groups. You can't just throw in ethanol and a carbonyl compound and expect the ethanol oxygen to add to a carbonyl. So we need a trick. And in this chapter, our trick that we're going to teach you about with oxygen nucleophiles is that if you want to get a weak, crummy nucleophile to add to a ketone or an aldehyde, we're first going to have to protonate that oxygen atom. We're going to have to add in powerful acids like hydrochloric acid, like sulfuric acid, like toluene sulfonic acid, which you should know how to make from electrophilic aromatic substitution. You're going to have to protonate that oxygen of the carbonyl using a powerful acid. And it's in equilibrium. It's hard to get a proton on there. Well, that carbonyl carbon does not want to be protonated. So it's not, you need powerful acids to do this. And so you'll end up protonating that. Not all of the carbonyl, maybe 1 out of every 2 or 1 out of every 10 carbonyls, depending on how acidic your conditions are, will pick up a proton. So you might have in your reaction only a small amount of this protonated carbonyl group. But once you protonate the carbonyl, it is super reactive. The carbonyl carbon is super reactive. Please do not ever, let me draw this lone pair here. Please do not attack the oxygen. Please do not ever attack that oxygen. It's already got 8 electrons, don't attack it. Attacking the oxygen will not take away the O+. The only way to get rid of that O+ is to attack the carbonyl carbon. I think that some people who take organic chemistry feel like, well, I always attack carbocations, which only have 6 electrons. That means I have to always attack things with positive charges. No, carbocations are reactive because they only have 6 electrons, not because of the positive charge. So attack the carbonyl carbon. That is screaming hot reactive on the carbonyl carbon. And here's the way we get rid of the positive charge on that oxonium ion. Oxonium means oxygen with 3 bonds. So we've got this, we're attacking this protonated carbonyl, and now it's so reactive, even an alcohol can attack that. And so we're going to see more, we're going to see these types of reactions happening in this chapter, where even a crummy nucleophile, like an alcohol or water, can add to, you know, I still have, if I see 3 bonds to oxygen, I have to put a positive charge there. So after the alcohol attacks, that is now an oxonium oxygen because it has 3 bonds. Okay, so we're going to see this, and this is going to do more chemistry that we'll show you later, this intermediate. This is all part of a longer mechanism that I don't have time to go through right now. Now, how do you know whether you're supposed to protonate the oxygen or don't protonate the oxygen? I'm telling you, you don't protonate the oxygen with alkylithiums because you don't need to protonate a carbonyl. Alkylithiums are so nucleophilic. But I'm telling you here, we're going to show you reactions where we have to add acid. How do you know whether you're supposed to include acid under the conditions of the reaction? And so I'm going to try to break it down to you by arranging the kinds of nucleophiles that you've talked about and that we are going to talk about in this chapter. And think about how the power of the nucleophile determines whether you need to add acid to the reaction or whether you can even tolerate acid during the reaction. Now, some of the most reactive nucleophiles that we have to think about are alkyl lithiums. So up here at the top of this list here, I've arranged these in terms of decreasing nucleophilicity, starting off with strong nucleophiles at the top and weak nucleophiles at the bottom. And we don't have good numbers for lithium aluminum hydride and sodium borohydride, for those hydridoaluminate and hydridoborate reagents. They're very reactive, probably not as reactive as alkyl lithiums, but we don't have numbers for those. The rest of these, I can give you quantitative numbers that approximate how nucleophilic and how basic they are. And at the top of this list, alkyl magnesium halides and alkyl lithiums are the most reactive. That bond right there is super nucleophilic. But what you'll notice here is that there's a difference depending on the hybridization. So I'll just give you a little pointer. Usually these things are so reactive that they're not important, but why should there be a 25 order of magnitude difference between this carbon and this carbon? 10 to the 25. 1 followed by 25 zeros difference in reactivity. It's not the sodium or the magnesium. It's because this carbon up here on top is sp3. This vinyl one is sp2. And finally, when we get down here to this alkyne carbon, it's sp hybridized. That hybridization, P character correlates with nucleophilicity. You haven't been using that information. It's been there the whole time throughout this whole course for the past 9 months, and you haven't been using it. And the differences are dramatic. So P character means more nucleophilic if everything else is equal. If it's 2 carbons and attached to a metal, you look at the P character. Okay, alkoxides are nowhere near as nucleophilic as these carbon nucleophiles that we learned in the last chapter. But all of the reagents that I've got here above the amine, So everything that I'm going to label in this green section, I want to make it clear that absolutely when we want to add these types of reagents to something, we avoid acid. You wouldn't want to put in acid with sodium methoxide. It would simply protonate the sodium methoxide. You don't put in acid or even water with alkylithiums. You avoid anything that has OHs in the, with alkylithiums. So you would avoid acid. You don't want to use acidic conditions there. There's going to be another set of nucleophiles, and that's amines and cyanide anions, where it turns out we want weakly acidic conditions. And I'm going to be very, very specific about what those conditions mean. Weakly acidic conditions. We're going to be using these nucleophiles under weakly acidic conditions. And then finally, when we get to oxygen nucleophiles means water or ethanol or methanol. When we want those to attack carbonyls, those are going to be occurring under strongly acidic conditions. Strongly acidic, hydrochloric acid, sulfuric acid, toluene sulfonic acid, which is just like sulfuric acid. We need strongly acidic conditions because this is such a weak nucleophile. The lone pairs on oxygen, we really need to make those help out oxygen nucleophiles. Let me go ahead and draw out mechanistically what's going on under those strongly acidic conditions and just remind you what I just told you before, is that if you want a lame nucleophile, like an oxygen lone pair, to add to a carbonyl, we've got to protonate that carbonyl. We've got to get a proton on that carbonyl in order to get this weak oxygen lone pair to add. So that's why we're doing these reactions of oxygen nucleophiles under strongly acidic conditions. The acid is there with the nucleophile. But once we get to stronger nucleophiles than that, the mechanism will be different. So in all these cases, like the cyanide group, the amino group, alkoxides, Grignard reagents, alkylithiums, all of those nucleophiles add directly to the carbonyl with no assistance. So for all of these reagents up here, they're so nucleophilic. Let me write a nucleophile instead of focusing on one. Instead of focusing on one class, I'll just write NU. All of these other reagents are so nucleophilic that we don't need to protonate the carbonyl. They'll just add right in quickly with fast rates and no need to protonate the carbonyl. You don't want to put in acids. If you put in an acid for these strong nucleophiles, it's simply going to protonate the nucleophile, and that's game over. So you need to recognize the cases where these exceptional cases where we've included acid under the conditions of the reaction versus ones where you absolutely want to avoid acids in the reaction. And it has to do with the mechanism for the reaction. Okay, let's go ahead and start looking at some of these recipes for using some of these nucleophiles. Let me just come back. We're about to start talking about the addition of cyanide anions to ketones and aldehydes, of amines to ketones and aldehydes, and then alcohols and water to ketones and aldehydes. That's the main focus of this chapter. And we'll also talk about this weird set of reagents that they crammed into this chapter that don't really fit that pattern. Okay, the cyanide, using cyanide anion as a nucleophile. I'm going to teach you how to make a functional group called a cyanohydrin. So we could take any nucleophile, or sorry, any aldehyde or ketone. I'm going to take benzaldehyde. There's benzaldehyde. And we can convert this into something called a cyanohydrin. And it looks like this. So I think you can tell we're adding the elements of H and Cn to that. So I'll talk about the stereochemistry in just a second. And we need secret conditions for this. The reagent that you use is not commercially available. The reagent that you use for this is hydrocyanic acid. We need this to get this to work. You can't buy hydrocyanic acid. So we have to make it ourselves. And the way we make this is we mix together sodium cyanide, it's a powder or it comes in pellet form, with hydrochloric acid. And we have bottles of hydrochloric acid and we have sodium cyanide in our sitting around in our laboratories. Now, in this particular case, you have to note the fact that we've created a new stereogenic center. And so I'm going to draw one of the two possible stereoisomers here, because I expect you to acknowledge whenever you form a new stereogenic center that wasn't there before. You have no control over that, so you're going to get both enantiomers. And so just make sure you acknowledge that. Now, we're kind of running out of time right now. When we come back on Monday, we'll talk about the mechanism for this reaction, but it's going to involve cyanide anion attacking the carbonyl. So, boy, we're really now deep into real organic chemistry where nucleophiles are attacking carbonyl groups. It's going to be the common theme for the rest of the course here. So we'll go ahead and talk about that in more detail when we come back, and I'll see you guys on Monday.